Welcome, my friends. In this video, I'm going to be graphing transformations of y equals sine of x and y equals cosine of x. A transformation of a graph is just some way that the graph can be manipulated, by either stretching it or shifting it or somehow changing the graph. Let's review the general form of these functions before we look at the transformations. The general sine function starts its period at 0, 0 and increases from there. At every quarter of the period, which is at every pi over 2 radians, we have an important point. At pi over 2, we are at the maximum of 1. At pi, we are at a 0. At 3 pi over 2, we are at the minimum of -1, and at 2 pi, we are back to 0. This function will repeat itself every 2 pi radians, which means that the period of pi is 2 pi. Cosine starts its period at a maximum at 0, 1. From there, we have an important point on the graph at every pi over 2 radians, which is 1/4 of the period of 2 pi. At pi over 2, we have decreased to a 0. At pi, we are at the minimum of -1. At 3 pi over 2, we have increased back to another 0. At 2 pi, we have completed one period of cosine, and then the graph will continue to repeat itself over and over every 2 pi radians. One of the most important things to remember about the graphs of sine and cosine is what they do at the beginning of their period. That can help you to find all of the key points. For sine, always remember that you start at 0, 0, and then from there we increase. For cosine, we start at a maximum, or in the case of the untransformed cosine function, we start at 0, 1, and from there we decrease. Try to see if you can remember those two basic pieces of information about the untransformed sine and cosine functions. The untransformed sine function starts at 0, 0 and increases from there, and the untransformed cosine function starts at 0, 1 and decreases from there. There end up being 4 common ways to transform either a sine or cosine function, indicated by the constants a, b, c, or d that can be included in the function. Typically, you won't have all 4 transformations in one function, although you could. More frequently, you will just have a few of these transformations. Let's talk about how having each of these constants individually will change the function. Note that in my general transformed function here, I have sine, but you could just as easily substitute cosine, and any of these constants would have the same effect. Let's first talk about how having a value for a changes the graph of the function. If you have a value of a multiplying your function, that will be a change in amplitude. More specifically, the absolute value of a, meaning the positive version of a, is what we call the amplitude. It's how far the function oscillates from the center, which is called the midline. In the untransformed sine or cosine function, the midline is just the x-axis. In either case, we are oscillating to 1 unit above to 1 unit below the x-axis, so the amplitude of the untransformed sine or cosine function is just 1. If you have a negative sign on the front of your function, that won't change the amplitude, but it will still change the behavior of the graph. More notably, the graph will do the opposite of what it typically does at the beginning of its period. For example, sine typically starts at 0, 0 and increases from there. If you had a negative sine function, we would still start at 0, 0, but instead of increasing, we would decrease. As for cosine, cosine typically starts at 0, 1 and decreases from there. But if you had a negative cosine function, instead you would start at 0, -1 and increase from there. If you have a value for b, a coefficient multiplying x on the inside of your function, that is a change in period. Typically, the period of sine or cosine is 2 pi. If you have a value for b multiplying x on the inside of your function, the new period can be found by taking 2 pi and dividing by b. If you have a value for c that is added or subtracted on the inside of your function, that's going to be a phase shift, meaning a shift either to the left or to the right. You will have a shift to the left if c is positive, and a shift to the right if c is negative. If you have a value for d either added or subtracted to the function, that amounts to shifting the entire function either up or down. The term for this is shifting the midline. So if you have a value for d, that represents a change in the midline of the function. If d is positive, the midline will be shifted up, and if d is negative, the midline will be shifted down. Remember, the midline is just the horizontal line that the trig function is oscillating around. Typically, we oscillate around the x-axis, but if you have a value for d, we will oscillate around some other line, either above or below the x-axis. Okay, let's take a look at some examples. We are asked to graph y equals 2 times sine of x. it looks like we have a value for a that is multiplying the function. Remember that having a value for a represents a change in amplitude. The coefficient of a equals 2 tells us that we have an amplitude of 2. That means instead of oscillating between 1 and -1, like the regular y equals sine of x function, the function of y equals 2 times sine of x will instead oscillate between 2 and -2. Everything else about the function will be exactly the same. Here is what y equals 2 times sine of x looks like. Instead of going up to 1 and down to -1 at our max and mins, we go up to 2 and down to -2. Let's try another problem. We are asked to graph y equals -3 times the cosine of x. Again, we have a coefficient multiplying our entire function, or a value for a. The absolute value of that coefficient is what we call the amplitude, so in this case, the absolute value of -3 is +3. This tells us that we have an amplitude of +3, meaning the function will oscillate between +3 and -3. We also must notice that this value is negative. If we have a negative cosine function, instead of starting at a maximum, we will start at a minimum. Typically, cosine starts at 0, 1. The -3 says that we will start instead at 0, -3. Summarizing, y equals -3 times the cosine of x will oscillate between -3 and +3, but will begin at 0, -3 instead of 0, +3 because a is negative. Let's draw the graph. We already stated that we are going to start at 0, -3, so let's put that point on the graph. Typically, cosine would start at a maximum and then decrease from there, but since we have a negative cosine function, we will start at a minimum and increase from there. We always have key points at increments at pi/2, so the next key point is going to be at pi/2, 0. From there, we will continue to increase to a maximum at pi. The maximum will be at 3, since the amplitude is 3. Then we will decrease at our next key point at 3pi/2 to be at 0. And finally, we will complete the period at 2pi, where we will be back down to -3. If we connect the dots, we will have the graph of y equals -3 times the cosine of x. Let's try another one. Let's say we are asked to graph y equals sine of x minus 2. In this case, we have a value for d, specifically -2. d equals -2 indicates a shift of the midline down 2 units. That means instead of oscillating around the x-axis, the graph will instead oscillate around y equals -2. Let's draw the graph. I typically draw the midline as a dotted line if it's not the x-axis, so that's why I have y equals -2 drawn as a dotted line. Typically, sine starts at 0, 0, but since we are shifted down 2 units, we will instead start at 0, -2. Typically, sine would increase from the beginning of its period, going up to 1 at pi/2. Instead, we will increase from our starting point of -2, so that at pi/2 we will be at -1. Then at pi, we will be back down to the midline, which is at -2. At 3pi/2, we will be at our minimum of -3, and then at 2pi, we will be back where we started, at -2. We can connect the dots to draw our sine function. This is the exact same graph as y equals sine of x, except for we are shifted down 2 units. Let's try another one. We are asked to graph y equals cosine of x plus 3pi/2. We have a value for c, which indicates a shift either to the left or to the right. A positive value for c indicates a shift to the left, and a negative value for c indicates a shift to the right. In this case, we have a positive value for c. c equals 3pi/2 indicates that the function is shifted 3pi/2 units to the left. Now, this is backwards for many people. Many people would like to believe that a positive value for c indicates a shift to the right, but it isn't. A positive value for c is actually a shift to the left. So why is that the case? Well, the way I think about it is cosine starts its period at 0. So what value would I have to plug into x to get to the start of my period? Well, I would have to plug in -3pi/2. If I had -3pi/2 here, I would have -3pi/2 plus 3pi/2, which would just be 0. So in other words, the starting place of the period is now -3pi/2, or 3pi/2 units to the left. So that means in general, whenever you have a positive value for c here, to get to the start of the period, you'd actually have to plug in a negative value equivalent to whatever this number is. So whenever you have a positive value for c, that actually indicates a shift to the left. The same exact logic applies to a shift to the right. So if you had a negative value here, you'd have to cancel that with an equivalent positive value, which would indicate a shift to the right. Let's graph our function. Typically, the cosine function starts at 0, 1, but since we are shifted 3 pi over 2 units to the left, we will instead start at negative 3 pi over 2, 1. Now for trigonometric functions, we have an important key point on the graph at every quarter of the period. In the case of cosine, the period is 2 pi, so 1/4 of that is pi over 2. That means we will have an important point on the graph at every pi over 2 radians. So what we can do is we can take our starting place of negative 3 pi over 2 and start adding pi over 2 over and over and over, and that will tell us the x values at which we will have important key points. If we do that, we will have negative pi over 2, 0, and pi over 2. Once we have incremented 4 times, that will create 1 period on the graph. Now, the cosine function starts at a maximum and then decreases from there. So since we are starting at negative 3 pi over 2, 1, at the next important key point, we must have a 0. We must decrease down to 0 at negative pi. So we have the point negative pi, 0 on the graph. We will continue to decrease to our minimum of negative 1 at negative pi over 2, the next increment. Then we will increase back to another 0 at 0. Finally, we will be back at our starting point at pi over 2, so we have the point pi over 2, 1 on the graph. Connecting the dots, we have the graph of y equals cosine of x plus 3 pi over 2. Let's take a look at this one. We have y equals sine of x minus 2 pi over 3. Again, we have a value for c, which indicates a shift of the function, either to the left or to the right. In this case, since we have a negative value for c, this is going to indicate a shift to the right. c equals negative 2 pi over 3, which indicates that this function is shifted 2 pi over 3 radians to the right. The period of sine is 2 pi, so we will have important points on the graph at 1/4 of the period, which is just pi over 2. In this case, the phase shift does not fall exactly on the period. Pi over 2 does not have the same denominator as negative 2 pi over 3. If the phase shift does not fall on the increment, you should find a common denominator. 2 pi over 3 is the same thing as 4 pi over 6. Our increment of pi over 2 can be written as 3 pi over 6. Now we have a common denominator. Let's graph our function. Typically, a sine function will start at 0, 0 and then increase from there. In this case, we are shifted 2 pi over 3 units to the right. So instead of starting at 0, 0, we will start at 2 pi over 3, 0. Instead of writing this as 2 pi over 3, I'm going to write this as 4 pi over 6 to match our increment of 3 pi over 6. We have 4 pi over 6, 0 as our starting point. From here, we need to increment 4 times to find additional key points on the graph and to finish one period. If we increment once by adding 3 pi over 6, which is the same thing as pi over 2, we will be at 7 pi over 6. Adding 3 pi over 6 again, we will be at 10 pi over 6, then 13 pi over 6, and then finally 16 pi over 6. Once you have incremented 4 times, you will have completed one period. Now we will have key points on the graph at each of these increments. We note that the sine function typically starts at 0, 0 and then increases from there. But in this case, we will start at 4 pi over 6, 0 and then increase from there. So that means at the next increment of 7 pi over 6, we must be at a maximum, which is at 1. So the point 7 pi over 6, 1 is on the graph. Then we will decrease down to 0 at 10 pi over 6. At 13 pi over 6, we will be at the minimum of negative 1, and at 16 pi over 6, we will be back to the x-axis at 0. Perhaps to connect this to the y-axis, I would want to increment one more time to the left. So if I subtracted 3 pi over 6 from 4 pi over 6, I would get pi over 6. Now, it's up to you if you want to reduce these fractions. I find it a little bit easier to keep them as an unreduced form so that they all have the same common denominator. If we connect the dots, then we will have the graph of y equals sine of x minus 2 pi over 3. Okay, let's try one final problem. We have y equals 3 halves cosine of x plus 7 pi over 6. In this case, we have two transformations in one function. We have a 3 halves that is multiplying the function up front, which is a change in amplitude, and we have a 7 pi over 6 that is added on the inside of the function, which indicates a phase shift. The absolute value of the coefficient multiplying our function is 3/2, meaning that the amplitude is 3 over 2, and the function will oscillate between negative 3 over 2 and positive 3 over 2. C is 7 pi over 6, indicating that the function is shifted 7 pi over 6 units to the left. Don't forget that when we add a value on the inside of the function, that indicates a shift to the left, not to the right. There will be important key points on the graph of a trigonometric function at every quarter of the period. In the case of cosine, the period is 2 pi, so 1/4 of that is pi over 2. We will have important key points on the graph at every pi over 2 radians. Just like the last problem, our increment does not have the same denominator as our phase shift. If that's the case, you should find a common denominator. Pi over 2 can be written as 3 pi over 6. Let's graph our function. Typically, the cosine function would start at 0, 1. Since we have an amplitude of 3 over 2, we would instead typically start at 0, 3/2. But we have a shift to the left, so that means instead of starting at 0, 3/2, we will instead start at negative 7 pi over 6, 3/2. From here, we need to increment 4 times to complete one period. If we increment 1 time, we would be adding 3 pi over 6, which is the same thing as pi over 2. Adding that to negative 7 pi over 6 would give us negative 4 pi over 6. Adding 3 pi over 6 again would give us negative pi over 6, and again we would get 2 pi over 6, and finally we would get 5 pi over 6. Once we have added the increment 4 times, we will have completed one period. From here, we can remember the general pattern of cosine. Cosine starts at a maximum and then decreases to 0 at the next increment. So we will have the point negative 4 pi over 6, 0. At the next increment, we will be at the minimum, which in this case is at negative 3 over 2. At the next increment, we will be back at 0, at 2 pi over 6, and then finally at 5 pi over 6, we will be back at the maximum of 3 over 2. We can connect the dots to complete our function. Alright my friends, that finishes this video related to graphing transformations of sine and cosine. In the next video, we will practice even more transformations, including a change in period.